Now that we've studied the idea of trigonometric functions and how they might be used in applications, we go back to our topic of derivatives and we try to study the derivatives of trigonometric functions. We're not going to do any proofs of the derivatives for trigonometric functions. We're just going to motivate them with a graphical approach. For example, here's the graph of sine of x. Notice it starts at 0 and then increases, and it has a period of 2 pi. All right, let's consider that to be our function, and then we're going to try to sketch the derivative of that function here down in the second graph. And so what we notice is, or what we remember, is that we have to ground our sketch of the derivatives by looking at the slopes on this graph and turning the slopes into values on this graph down here. And it's very easy to anchor yourself again. What's the most obvious slope on a graph? A slope of 0. A slope of 0 turns into a, what y value do I get? A y value of 0. Slope of 0, this is a flat line, gives you a dot, a value of 0 here. Likewise at these 2 points as well. What happens in between these two grounded points, this 0 slope and this 0 slope? Well, we have positive slopes. And that means down here, we must have positive values. Again, slopes, translate them to numbers. Those are the values that we plot on the y-axis here. And the steepest one is in the middle. And while this is not obvious, maybe it's not too bad. There's a 0.11 around there. This slope right here in the center actually turns out to be exactly 1. So we can actually get another grounding point on our graph here. So we have positive slopes with a particular value at the middle, and so we might sketch something like this because it looks fairly smooth. And not too surprisingly, if the slope is 1 here, the slope would be -1 here, just for the apparent symmetry. Slope -1, and so we get a value, a y value here of -1. It's up a bit there. And we sketch that out, and we start to see, of course, it's going to have the same periodic structure as the graph above. And based entirely on our graph of the original function and our interpretation of slopes being translated to values giving us the derivative graph, we get this graph, and without too much exercise, I think we can all believe that that is the graph of cos of x. It starts at 1, goes down, then goes back up. The amplitude is 1. That's a little less easy to see from a sketch like this, but it doesn't seem unreasonable that the derivative of sine of x will end up being cos of x. Well, that's fortunate. And notice it also depends on the radians. Here's where that radian measure is so important. I said that this initial slope was 1 because this gap from here to here is 1 radian. If you change it to 1 degree, 1 degree is actually about there, and so you'd have a slope that's much, much, much smaller if you look on a short interval like that. So we need radians to make this work. We'll leave it at that for now. And here to immortalize that, the derivative of sine of x is cos of x. It's not a proof, but it's a pretty strong argument. To generalize that, we could do similar things, or we could do more algebraic approaches to identify these other derivatives. The derivative of cos is, notice the negative sign here. Derivative of tan is secant squared. And remember that secant of x is 1 over cos of x. These are one of these relationships where it's the sec goes with the cos, and the cosecant goes with the sine. They're inverses in 2 different ways. And cotangent, cosecant. The big ones are cosine and tan, I would say. Those are the most commonly used 3 derivative rules. Let's put them into practice. If we're going to use the cosine rule here as well as the chain rule to actually prove some of the later ones. So it's also worth noting that if you know the derivative of sine and cos, you can find all of these other derivatives, because all of these functions are just combinations of sine and cos, products, quotients, and relationships like that. So for example here, if I wanted to go from the simple rules for sine and cosine and find the derivative of secant of x, we could do that simply by remembering that secant is 1 over cos of x. And then what we could do is recognize this is a quotient, but the constant in the numerator means the quotient rule is overkill. Another option before we differentiate is to rewrite as a power. If we do that, we're going to have cos of x to the negative 1. And then if we think back to our earlier rules about derivatives, this is a chain rule. The derivative of anything to the negative 1, that's a power rule. We're going to get the same thing to the negative 2. So cos of x to the negative 2 times the derivative of the inside. And the derivative of the inside is negative sine of x. So if we simplify that, we're going to have a negative and a negative cancel, plus plus, and we're going to have a sine of x in the numerator and a cos of x all squared in the denominator. Now, that doesn't actually look like what we just saw on the last page. On the last page we said the derivative of secant was secant times tan, but that's not what we have here, at least at first glance. If you remember the different properties, we said secant, as a reminder, is 1 over cos, and tangent is sine over cos. So if we simply repackage what we have here, we have 2 coses, so we can break it into 1 over 1 cos times sine of x over the other cos. Same thing, cos times cos would be cos squared, sine times 1 would be sine, and this is secant of x times tangent of x. So from the question, what's the derivative of secant of x, just using the identities, what is secant, what is cosine, what is tangent, and the derivative rule for cos, we can get the derivative of secant. So it's worth noting that the derivatives of sine and cos are the most fundamental derivatives that you'll need. Everything else you can derive if you have to in a pinch. Just as a practice exercise here, bringing all the rules together, take a look at this derivative and ask yourself if you could evaluate it. All right, we'll take a quick stab. Don't get lulled in by this 4 out front. Remember that the derivative of a constant is always 0 if it's a constant by itself. So if we're trying to find the derivative of 6 cos of pi x squared plus 1, all of that, then the derivative of the 4 is 0. The 6 is a constant multiplier, so we leave it alone and find the derivative of this. The derivative of cos anything is minus sine times the same thing. That's our chain rule. But times the derivative of what was inside. So times pi times 2x plus 0. And what does that turn out to? It turns out to be 6 minus sine. All right, let's take a look down our scan here. Minus 6 sine pi x squared plus 1 times the 2 pi x. Exactly. So our answer would be 3 here. So with this enlargement of our derivative rules to include the trigonometric functions, we can also bring the trig functions into our rules about chain rule, product rule, and quotient rule, and apply them all in combination now.